Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at continuity. If you like this video, feel free to click the like button. You can also comment in the comment section and share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comment section of the intro video, including this one. We have that polynomial functions, they are continuous, period, continuous everywhere. Rational functions and radical functions will be continuous on their domains. Also, we're given what is a definition of continuity at a single x value c. Namely, we need for continuity at x is equal to c, the limit of the function at c is the function value. There's also some additional information here. A theorem is provided about sum and difference functions, product functions, and quotient functions that we might use in our work today. There's also definitions of the concepts of removable and non-removable discontinuities. Let's take a look at the first problem. It reads, give the three conditions that are necessary for the function f of x to be continuous at x is equal to c. So the way we'll answer this question is we'll write simply this definition for continuity at x is equal to c. So we need, as x goes to c, of f of x to be equal to f of c. And in particular, one is that the left-hand side of this statement exists, meaning it's a real number. Two, well, the right-hand side of this statement exists, it is a real number. And three, which is the two quantities left and right-hand side are equal. Provided these conditions hold, we have continuity at x is equal to c for this function f. Let's go ahead and move on. Let's try this next problem. It reads, from the graph of f of x given below, find the values of x where f of x is discontinuous and state all conditions above that fail to hold. State whether the discontinuities are removable or non-removable. So we can see that the discontinuities are occurring at 1, 3, 4, and at 5. So there is a break in the graph of some type at all of these x values. Here at x is equal to 1, we say this type of discontinuity is a jump. Okay, so there is a jump discontinuity. And at jump discontinuities, the limit of the function will never hold. The function value may hold if you have a closed circle point where one of the pieces of the graph either picks up or here ends its behavior. So in this particular case, there is a function value. It is 2 at x is equal to 1. So we can say that that the left-hand side exists, that one fails to hold, and so does 3. Okay, we can say similarly at x is equal to 3, we have a hole. The function has been defined to have a different y value other than the y value where the hole is. So because of this, we can say that the limit, it does exist, as when you're approaching 3 from the left and from the right, the y values are tending to 7. So I is fine, double I is fine as well, but triple I statement fails. It's good to understand here why we don't have the discontinuity. So this fails. Okay, at x is equal to 4, we have a hole, and the function has no function value at 4. So we can say that at this hole, similar to above, 3 is going to fail, but also 2 fails in this case. Okay. Finally, we have at x is equal to 5. Well, we have an asymptote. There is a vertical asymptote, and at a vertical asymptote, we will not have continuity. And we can say the reason why we have discontinuity at x is equal to 5 would be, for one thing, the limit doesn't exist. Because when we say the limit exists, we're saying it's a real number. Minus infinity doesn't count. So I fails. There is a function value at 5. You can see it's a closed circle point, y value of 3 at 5. So 2 is okay, but because the limit doesn't exist, 3 doesn't hold. For that statement that the left-hand side is equal to the right-hand side, you need real numbers on both sides of that statement. And the left-hand side is minus infinity. It's not a real number. So this. Now, as far as whether these discontinuities are removable or not, it depends on the convention you're using. So here, if you're allowed to redefine the function at the discontinuity, including the ability to delete a point on the graph, then we could say that the discontinuities that are removable are the ones at x's 3 and 4. If you're not allowed to delete a point, so if you're not allowed to delete, for instance, the point 31 from the graph, then you could not remove the discontinuity at x is equal to 3. So we'll go ahead and solve this problem with the convention that we can delete a point. If we want to remove the discontinuity at x is equal to 3, we get out the eraser and we delete the point 31 and redefine the function to have the function value 7 at 3. So we fill the hole, okay? Likewise, if we want to make the function continuous at 4, 5, and we have the power to do so, we'll just fill in the hole there, okay? So removable discontinuities in this convention would be the ones at 3 and 4. You want to check with your teacher for your course as to whether you are given license to be able to delete points from the graph. The other convention, which is you're only allowed to fill in points, as in like define but not redefine, that would tell us that here at 3, you cannot remove the discontinuity because by filling in the hole, you no longer have a function because you couldn't get rid of 3, 1. So please note here the difference in the conventions and make sure that you're using one that is used by your teacher for your course or in your textbook, because not all authors agree on even standard things like how to remove a discontinuity. So we'll go ahead and take our solution to be here, the solution where we can indeed remove points from the graph. Let's go ahead now and push on. So we want to look at next problem number 2. We're given a piecewise defined function, and we want to find the value for the constant k that will make the function f of x continuous everywhere. So we know to be continuous at x is equal to any value, like c, we need the limit and the function value at c to be the same. In this case, the function is behaving like a parabola when x is less than or equal to 2. Parabolas are polynomial functions. They are continuous on their domains. And it's behaving, we can see, like a linear function when x is greater than 2. Also a polynomial function, so continuous on its domain. So the only question is, when the behavior changes at x is equal to 2, do we have a jump? Is there some sort of hole? What's going on? So in this case, we're going to go ahead and state for continuity at x is equal to 2, we need the limit as x goes to 2 to equal to the function value f of 2. We can actually see from the definition of the function that f of 2 is going to be given by the parabola behavior, because when x is less than or equal to 2, we behave like kx squared. So we should plug in 2 into the kx squared expression. The 2 plugs in for the x, so this gives us 4k. Okay. As far as the limit is concerned, we could do the limit from the left or from the right. They need to be the same. So the limit from the right is going to be obtained when we're behaving like the linear function. So it is apparently going to be 4 plus k. The limit from the left is going to be 4k as well. So there's really no need to append equal to another 4k. It'll be redundant, saying 4 plus k is equal to 4k, which is equal to 4k. I think here it's pretty clear that there is a value for k that will make this statement true. We solve this little linear equation. 4 plus k is equal to 4k. And we find that 4 is equal to 3k, which in turn implies that k all by itself is 4/3. Okay, and that will be the value for k, so that the function is continuous at x is equal to 2. We argue that the function is continuous elsewhere, so we can now conclude that by choosing k to be 4/3, the function will be continuous everywhere. Okay, and that is our conclusion. So with k taken to be 4/3, we have that f of x is continuous, period. Okay, continuous meaning continuous on its whole domain, which would be the whole set of real numbers in this particular case. Okay, in the next problem, we have the directions: find the values of x at which f of x is discontinuous. Use interval notation if possible to describe the set of values where f of x is continuous. So here we should go ahead and first state where we are discontinuous. For a is a quotient function. The exponential function in the numerator is continuous for all real values, and the denominator is continuous for all real values, except being that that denominator could be 0, and it is 0 when x is 2, that x value of 2 is not permitted. So we'll say here that we have a discontinuity at x is equal to 2. Likewise, for b, we can say that a discontinuous function on the entire interval for which the ln function is not defined, that will be from -infinity up until 0, including 0, since the domain of that function is from 0 on up, not including 0. So you cannot evaluate log of 0. There is no function value. For c, we have a cotangent function, which has a sine function in the denominator. So using our knowledge of the unit circle, we can go ahead and state where this cotangent function would be undefined. So the sine function is going to be 0 when x is equal to 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. So we can say that this function is discontinuous at x is equal to plus or minus 3 pi, and the pattern has been established. You could use here a shorthand, i.e. x is equal to k pi, where k belongs to the set of integers. For part D, we have here a function which is a quotient of a root function and a polynomial function. So this function is going to be discontinuous where the numerator is not a real number. So that is on the interval from -infinity up until 5. And we would not include 5 there because 5 is actually okay to plug into the numerator. It would give you a 0 in the numerator, which is okay, of course. And there may be some x values as well that make the denominator 0. We can go ahead and do a little pencil factoring here. The denominator factors into x minus 3 times what is x plus 1. So there are two values that make the denominator 0. It would be positive 3 and negative 1. So we should say here that x is equal to positive 3 and negative 1 are part of that set of values where we're discontinuous. We cannot permit 0 in the denominator. It may be that there's a little redundancy here because the value minus 1 is certainly in the interval from minus infinity to 5, and the value 3 as well is in the interval from minus infinity up until 5. So that means that we can actually, in retrospect, kind of just delete here this excessive information because it's already quite clearly stated in the interval given. Now, for part E, we have a function which is just a polynomial function. And what could be nicer than a polynomial function? This is nowhere or never discontinuous. Okay, at no place is it discontinuous. Polynomial functions are continuous on their entire domains, which is the whole set of real numbers. Now, we were told to use interval notation if possible to describe the set of values where we're continuous. So let's try to do that here. We can say that for the case when there was a discontinuity at x is equal to 2, that means we're going to be continuous on the interval from minus infinity up until 2 union the interval from 2 to infinity. Given that we're discontinuous on minus infinity to 0 inclusive, that would mean that here we are continuous on what is the open interval from 0 to infinity. For this one, we could say that we are continuous on, it's going to be a little bit tedious to write this, but dot, 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 the interval from minus 2 pi minus pi, which we should use here, open interval notation, union from minus pi up until 0, union from 0 to pi, union from pi to 2 pi. And we can do maybe like a dot, dot, dot to indicate that that pattern extends in both directions indefinitely. And finally, for this one here, assuming no blunders, we would say here that we're continuous on, well, what is left from the set of real numbers. If you take out the interval from minus infinity up until 5, we'll have from 5 to infinity. Given that I am only human, it is possible that there are errors in my solutions. If you find an error, I encourage you to leave a comment in the comment section. And as always, I'll do my best to weed out the errors in advance. But again, being human, it may be inevitable that somewhere along the lines, Dr. M says 1 plus 2 is 4. So here, for state where the function is continuous, we can say for part E, we are continuous on what is the entire set of real numbers in interval notation. There that is. And with that, we have solved yet another worksheet. Again, if you like this video, feel free to subscribe to my channel and follow my other videos on learning calculus through worksheets. Thanks and goodbye.